So just to recap, conservative forces are forces that when they do negative work, which means that something is transferring energy to them, they actually store that energy, and that energy becomes potential energy. And that potential energy can then be used in the future, and that energy can get kind of given back by that force. So if I lift up a ball, gravity does negative work. In a way, I'm like kind of like charging it up or kind of winding up gravity. And now the ball has a height, right? Now that the ball has some like elevation, now gravity's like, okay, now I can do work on you, right? Instead of you doing work on me, now I can do work on you. But I cannot do work on you until you do work on me, right? And that's just saying that until you lift up the ball cannot fall, right? And the more you lift up the more the ball can fall. And that makes sense. So let's do an example where we can see that potential energy being built up and then released and converted to kinetic energy. So if I have a ball, and we'll use gravity because it's the kind of easiest example. And say we lift it up 10 meters. So if I want to figure out the work I have to do to bring it up to 10 meters, the work done by me is equal to the force I have to apply, which is actually enough force to match gravity. So that's going to be for a 1 kilogram ball, mass times acceleration due to gravity, times the distance, 10 meters. So we'll get 98.1 joules. And that's how much work I have to do to get the ball from point A to point B. But in doing that, gravity does negative work, right? It's just going to do the negative whatever I just did. And that's because the force of gravity is going down, right, with a magnitude of 1 kilogram times 9.81 meters per second squared. But because the ball is going up and the force of gravity is going down, the work is actually going to be negative, okay? So then we end up with negative 9.81 joules. And we see that in the work energy theorem, the work net is the change in kinetic energy. And our net work in this circumstance, 98.1 joules plus negative 98.1 joules, is 0 joules. And that means that although I'm applying a work to this ball, right? I'm doing work on the ball. I'm transferring energy to the ball. We do not see that energy show up as kinetic energy, right? Right? I'm moving the ball up, but it's going at a constant velocity, right? And even we can say that when the ball stops, it has 0 kinetic energy. So I'm not actually getting the ball to speed up at all. So where does that energy go that I'm transferring to it? Well, because gravity is a conservative force and it's doing negative work, that is actually where the energy is going. And if I find my change in potential energy, which is the negative force times distance of a conservative force, for us that's going to be the negative of the work we got up for gravity. So negative 90.1 joules, and that'll give us 98.1 joules. And now that this has 98.1 joules of potential energy up here, and that's assuming, right, that the ground down here has 0 joules of potential energy, right, because the ball has no potential to do anything when it's sitting on the ground. So we lift it up to change of positive 98.1 joules, so the ball has now gained 98.1 joules. Now what does that mean? Well, when the ball was on the ground, how much kinetic energy could it have gained from gravity? Like none, right? There was no distance for it to fall. Well, now we've given it a distance. So now if we let the ball fall, and now the ball is going the opposite direction. Let me see if I can get another color in here quickly. Now, the work done by gravity is going to be positive. 1 kilogram times 9.81 joules times 10 meters, and we'll get positive 98.1 joules. Right, and this is now the only work being done, so the work net is 98.1 joules, which means that that's how much kinetic energy it gains. And that kinetic energy was transferred from potential.